So here is the doubly fed motor we'll be testing. As you can see, it is connected to two electrical ports through which the power enters, and we can access both the stator and the rotor windings. On the same shaft you can see this permanent magnet generator which is attached, and this acts as a load to this doubly fed motor. And we have connected an electrical load bank at the terminal of this permanent magnet synchronous generator. Based on the current command, it loads the shaft to the motor. The stator of the doubly fed motor is connected to this ACR based transfer switch. So it has 12 thyristors which enables the stator to be connected either to the AC source or to the DC source. And this is a programmable system on chip board which communicates with the drive-in converter and figures out when is the right time to switch between the sources, such that there is no shorting between the sources, as well as the load is not disconnected even for a considerable amount of time. This is the stator and rotor current measurement unit, as well as it measures the AC source and the DC source voltages. The measured data is fed through two channels, one to the drive-in converter, which can be seen here. So this is a TI high voltage motor control kit, and this has been modified by us so that we can tap off the required voltages and current signatures and do a communication between the drive-in and the front-end converters. As well as it has been modified so that the ADCs can measure the correct parameters required for the control. And the other data which comes from the current measurement unit goes to this 16-channel data acquisition system, which is a lab jack. And later on we collect this data to our separate computers for offline analysis as well as record. This is the annunciator panel. So it has 12 LEDs, as you can see, the main ones, the green on the left and the yellow on the right. So when the stator of the DFM is connected to the DC source, the 6 LEDs on this side, the yellow ones, turn on. Each indicates the thyristors which I showed earlier. And when the stator is connected to the AC source, the green LEDs turn on. There are additionally 3 more LEDs, the red ones, which indicates whether the phase of the AC source is reversed, and this is required for full negative speed operation. And the other 2 LEDs are mainly contactors for protection. The drive-in converter, as you can see here, is connected to a DC bus which has a braking resistor, and this is the switch for the braking resistor which turns on when there is a dumping of power to the DC bus. And the braking resistors are connected here, as you can see. So this is a bunch of resistors which dissipates power when the DC link bus voltage goes higher. And the DC bus voltage is made from this front-end converter. So this is again another TI HV motor control kit which has been modified like the one which is at the drive-in. And you can see all the parameters we can measure and control on this case. And the controller which we are using here is TMS F28035. So this is the grid side converter, and also you can see this is the grid side filter. So it's an LCL filter which has 3 inductances for the 3 phases on the grid side, then the capacitor bank, and finally the inductors on the inverter side. Similar to the drive-in side, we have a current measurement unit here also, so which measures the grid side and the inverter side currents as well as the voltages of the grid that is required for the control of the grid side converter. And the input to the grid side filter comes from this auto transformer. This is almost like a fixed transformer. We don't change the turns after the initial design. So this just isolates and gives a proper voltage to the front-end converter. So we need to send the power both to the stator switch, which connects to the AC source, as well as to the front-end converter. And this is the point of common coupling you can see here. And this contactor basically connects the AC source to this point of common coupling. And the AC source comes all the way from using this transmission line, apparently this transmission line, and from this generator set. This generator set, as you can see, there are 2 generators, the blue ones here, which are driven by DC motors connected in series with the shaft. and driven by a belt pulley arrangement. So we control this generator using MATLAB Real-Time Workshop, and so it behaves like these prime movers are controlled both with respect to the speed as well as the field windings on the generators are controlled from this power source, which is commanded from the MATLAB Real-Time Workshop. So the overall setup basically consists of these generator sets which are operated in parallel, which goes through this transmission line using that black cable, and the power comes to this side of the bus, and this is where the front end converter is with the auto transformer, and this is the point of common coupling. This is the load bank you can see here. So this is which was connected to the permanent magnet synchronous generator, which is at the DFM shaft, and this is followed by the drive end converter, the data acquisition system, the current measurement unit, the transfer switch, and finally the power goes to the WFED machine, which was our prototype. So that's the overall setup, as you can see. And of course, this is the control panel with which we can monitor and control all the things, all the machines and all the inverters. So this is the drive end converter panel. So this is a Code Composer Studio window, and similarly we are using this for the front end converter. This monitor, you can see this is the load bank, and you can see this is the load torque speed characteristic we can plot real time. So this is again done by in NI LabVIEW. And finally on this side you can see the MATLAB Real-Time Workshop for to control the generators. So we can control everything from this setup as well as the data acquisition systems. So now we'll start the generator first. So we will now put the AC source into the bus. So now we have turned on the contactor here, as you can see, and this has given the AC source both to the front end as well as to the transfer switch by this, as you can see, by this AC waveform. So the next step is to produce the DC from the front end converter using this AC power. So the yellow waveform which you see is basically the DC source voltage, and we will activate the front end converter now. So now it's pre-charged, the DC bus voltage, and now it's controlled at 120 volts from the front end converter. So now we can turn on our drive end converter. So right now the DFM is in 0 speed, so that's why the right LEDs are glowing, which implies that it's in DC mode. Also you can see the waveform of the stator current, which is shown by the green here. It's basically a DC, implying that the stator is connected to the DC source. So now we'll give a step command in speed, and let us observe the waveform. So the blue waveform is basically the rotor current A phase, the green waveform is the stator current A phase, and the yellow waveform is the AC source voltage. So we'll see how it transitions from the DC mode and AC mode as we ramp up the speed. Current instantaneously became a fixed frequency AC, implying that it's running at AC mode now. And this you can see here also in the annunciator panel now. The AC source is connected to the stator. So let's observe the transition on these LEDs as we do an AC to DC transition when we ramp down the speed. went to DC mode and the loading also got reduced. As you can see here again, the waveforms are DC in the stator, the green current. Let's look at the front-end converter waveform as we are ramping down and ramping up the speed. So the yellow waveform here is the DC link voltage, which is maintained at 120 volts. The green is the AC grid voltage, and the violet or the blue are basically the current drawn by the front-end converter. So we did a ramp step command in reference speed from 0 to 0.5 per unit RPM and again back to 0 RPM. So let us look at the shaft as we do a step command in speed, and we do again go to a reverse speed also in this case. So we'll give a step command in reference speed between 0.5 per unit and -0.5 per unit. We saw that the shaft doesn't see any pump or it's seamless transition between any of the modes. We can't figure out whether it was running in DC or AC mode. We'll do the transition once again, looking at both the LED as well as the waveform together. So we saw the transition between DC and AC mode and full speed RPM. Now let us look at the load profile. So we'll see how the load profile changes on the left curve here. So let's give a step command in speed. So you can see the quadratic curve, which is basically loading the generator with a constant current load. Will capture the data, and so we are capturing the data using MATLAB here, and soon the data will be plotted real time. In the meantime, you can see these are the controllers and the parameters which we are monitoring on the drive-in converter and also on the front-end converter. So we have plotted the waveforms here, and you can see these are the stator current drawn for the step up and step down command. This is how the rotor current was controlled, and this is the most interesting one. You can see here, this is the torque speed profile with respect to time. So the blue is basically the speed we measured, and the black is the torque we measured. As you can see, at the instant of transition, it's bumpless. It's only the noises which you can see here, which can be pretty easily filtered. So you can see easily that the torque, so the DC mode torque command is designed to be at lower value compared to the AC mode torque command. So that's why you see a step in change here. Otherwise, it's a bumpless transition on the torque. This is how the power was was drawn. So this is the black is basically the DC link voltage, which was pretty stable, except at some points here but it is within the bound expected. And also the green curve shown here is the power which is drawn from the generator. And as you can see, as the speed ramped up, it was also bumpless, and the generator didn't see any bump in the power drawn by the overall drive. So it was bumpless both on the drive side as well as on the generator side. Next, we will run the motor at 1800 RPM. Step change in load command. So right now the operating point is here, which is at rated speed and rated torque, and we will emulate a pulsating load torque. So right now it's emulating like as if the propeller is going out of the water and coming back in. So this is one of the harshest tests again we can do on the shaft. So as we stop the setup, you can see here we are throwing off the bus voltage, and again we can plot all the parameters from the MATLAB. So you can see here the power supplied by the generators. So the pink is one of the generator and yellow is the other generator, and the sum total is the blue one. And this was essentially the point where we loaded the generator in a pulsating manner, going from like when we were emulating that the propeller is going in and out of water. And this is where we ramped it up from 0 to 1800 RPM.